Thanks. I appreciate the opportunity to come talk to you about this work. So I'm actually going to wind up trying to cram 2 talks into one little slot and get you out of here early for lunch. And so they're both broadly focused on materials related to LC3. And so I'm not going to obviously spend a lot of time with this audience on the rationale for it, but I wanted to make sort of 2 general points. The first is that there's a need to, these are very complex materials, and there's a need to find methods for optimizing their behavior in the middle of a much broader range of feedstocks that go into these formulations. And then the second is this general question of we would like this material to perform in every way possible like Portland cement. And so how can we develop ways to predict what the performance will be in various ways, and then B, how do we adjust it and without making the problem even harder, which is unfortunately what happens when you wind up adding additional components. So in terms of optimizing the performance of LC3, the sulfate balance is one of the most important factors. And so it's been shown for a while known for a while that adding sulfate is necessary to optimize the compressive strength of this material. And so there are going to be trade-offs in terms of the formation of carboaluminate and ettringite. And so it's been known that you're always trying to do this kind of balancing act between these, that you don't want to, if you don't have enough sulfate, you'll get very rapid formation of some of these phases, and the ultimate strength winds up being weaker. And so there's been this a connection with the formation of sort of the staging of the silicate peak and the illuminate peaks that's observed in calorimetry as shown here. And so if we have, again, we'd like it to look sort of more orderly like the reference OPC sample. However, if you have an LC3 that has no gypsum added, you see this spike in the illuminate peak, and ideally you've got this at least an hour in between these peaks. And so the question is, how do we come up with a strategy for dosing this appropriately? We believe that it's related to the sulfate content. And so this is just typical, these are typical data shown here, and this is for Portland cement. But then the question is, like, what I would like to do is apply a data science method like machine learning. What can I grab onto here in order to kind of figure out, well, is this ideally sulfated? And if not, how do I, which direction do I need to shift? And so the approach that Oljan took, who was the PhD student that led this work, is started focusing on using some of the slopes of these curves as a signature for some of the subtle events that are happening here. And so, because the questions that we really want to start asking or be able to answer would be, when does the acceleration start exactly? And then, what is the best way to calculate the slope following acceleration? And then, how do we identify the sulfate depletion? And so, his hypothesis really was that he can estimate some of these kinetic parameters using basically using a combination of kind of general data science approaches, but then focus the search on using kind of derivatives of these curves in order to identify these important points in them. So the methodology, Oljan did the experiments by and large himself, or with help from the undergrads at Georgia Tech. And so it winds up being a large screening here. Some of the limitations of this are he's only using the highly pure clays that are found in Georgia, and then we're only using one type of Portland cement, I think from Argos, but then looked at a lot of different variables on top of that, particularly looking at things like particle size, because there was a sense that this is going to be an important factor in terms of governing the kinetics of a lot of these reactions, which we know are in part determined by the exposed surface area. So I'm not going to go into a lot of details in terms of the computational methods, but he basically needed to use a kernel regressor to basically smooth out the curves, because we're getting our discrete data points, and he needs to be able to calculate derivatives continuously. So this is, some of the details are in the paper that we published based on this work. But essentially what you wind up getting are, based on this kernel estimator methodology, you start to get very accurate estimates for the time of the max. So basically features like identifying the slope of the silicate peak, the times associated with the maximum of the silicate peak, the sulfate depletion point, et cetera. And what this does is, if our goal is to get this sulfate, this window of at least an hour, what it does is it allows us to then very quickly take the raw data coming out of the calorimeter and determine where we are in terms of this sulfate range. There's obviously a lot of other things going on at the same time. And so the approach that we take for machine learning is broadly shown here. And so rather than listing, what you need to do is you need to identify every sample, and then you associate that sample with certain outcomes. And so you're trying to make a function that will relate input to output. While it sort of makes sense to just list the compositional variables directly, in reality what that does is it can wind up requiring much more data than is feasible to actually get. And so the method that we've adopted in machine learning is kind of an example of it is shown here. And so rather than listing out, I used like this cement and this metakaolin and this limestone, what we do is we start listing things by what we refer to as latent variables, which are, they're going to be basically allow us to make connections with theoretical constructs. So where we say, well, we know that particle size matters, and so why don't we use this as a variable in our model, also known as a feature. We featurized it by just the fraction of metakaolin, and then a few different parameters that that related to like solid volume fraction, so solid volume concentration. And in this case, we were wondering if superplasticizer content mattered, and then of course sulfate content. But the idea is that we think that all of these, our hypothesis is that multiple variables are going to matter here, and what machine learning lets us do is kind of hold on to some of the complexity and then compare the results against the data that we actually have. So, in comparing the results from an undersulfated mix, where we see very rapid ettringite formation compared to the properly sulfated mix, what he's done is he's featurized these according to some of these derivative plots, and what you're seeing is, and specifically tied them to the kinetics of forming certain phases. And so what we're seeing here is a much more, when we achieve the sulfate balance, what we're getting is a much more orderly formation of these phases, rather than sort of rapid depletion of some and formation of others. So, some of the key findings, it's not surprising that sulfate is the most important compositional predictor. But what we found was that the more water, the greater the water to solid ratio, the higher the sulfate balance that was required to maintain these kind of kinetics. And that we were seeing a strong competition exist between the metakaolin fraction and the fineness, so like factors related to particle size, and determining this depletion point. Again, it's all going to be driven by the kinetics of the process. And then finally, in this particular system, we're working under fairly narrow conditions. The effect of the superplasticizer actually appeared to be less important than some of these other factors in determining sulfate balance, which may or may not be surprising. And so when we look at sort of the variables and their relative contributions here, again, what we're seeing is, in machine learning, we generally assess models by what are called parity plots, which are a plot of, on the x-axis is the actual the sulfate balance, and that's the number of hours in between these points on the curve, and then that which the model is actually predicting. What we're seeing is, for both the training part and the testing part of model development, we're seeing good agreement, suggesting that the model is sort of latched on to the fundamental characteristics that determine this. So this was work that was funded by RPE, Olgens on the back left there, and so that concludes the first part of the talk. The second part is a broader program that Kim and I got involved with, and I wanted to acknowledge Daniel Ben-Kieser, who's now the postdoc, who's leading sort of our part of the work here. But it's a multi-university collaboration being led by Keishan Wang at Iowa State and funded by Federal Highway. And so the goal is to really start using, is to help Federal Highway really start using some of these much more complex materials in things like pavements and bridge construction. And so for reasons that I can only guess, we refer to these as not LC3, but calcine clay, type 1 limestone cement, limestone cements. So CC1L cements is what we're calling them here. And so part of the reason is that we're considering a much broader range of natural pozzolans, kaolin being an important example, but that we're actually trying to source materials from around the country to get a more comprehensive view in terms of, again, getting to the second question of how do we get a much more complex cementitious material to kind of behave more reliably like Portland cement. And so the workflow is shown here. So there are multiple steps. My role is relatively limited in terms of much more looking over the shoulder of people doing some of the material characterization. But then, but really, I come in more the part related to materials discovery using machine learning, and specifically starting to build models that are not just that don't just explain, but can also help us design. Okay. So just moving through quickly in terms of what how the workflow goes. So in task 1, and so this is Maria Younger's group at Texas is leading a lot of this in terms of just characterizing raw materials, getting raw data in terms of and making some of these early blends of paste to explore the different combinations. Essentially, what we're doing is we're using this as the basis for training the model that we're using, or that we're going to develop. And so then we start feeding these into algorithms, and I'll tell you a little bit about some of the early work here. In some ways, this is just kind of the advertisement or the introduction to the broader project, where this is going to feed in. But the idea is, certainly we're still here very interested in things like ultimate sulfation level, optimal sulfation levels. But really, the idea is we want to be able to inform mixture design such that based on certain set of cement characteristics, pozzolan characteristics, and limestone characteristics, how can we make these CC1L cements in order for these particular applications? And then finally, just some performance testing. And so this is really kind of, again, the goal is to take a much more complex range of input ingredients and start to predict a number of different important properties such as set time, slump, air content, compressive strength, etc. And so when I say concrete, we've been more focused initially on mortar. The concrete work is mostly just happening at Iowa State, and for obvious reasons, it's going to involve a much narrower range of binders. And so when we're looking more broadly at sort of the role of binders and their effects on something like concrete, we actually look at mortar. So there are a number of different possible process variables. And again, you could build a machine learning model that is going to be parameterized by each one of those, but what we're hoping to do is identify, in order to say, just because the types of the cements themselves could be different, the pozzolans will be different, et cetera, we'd like to have a more fundamental representation of what is it about them that leads to the differences. And then based on that, if we build a model, it should, in theory, be able to generalize to a much wider range of possible systems. And then in this case, we're really just initially focused on compressive strength and mortar flow. Daniel actually has a folder with 27 different databases that he's building, and so he'd love to tell you all about that. He's in the back, and so don't let him leave if you want to ask any questions. So this is kind of where ONSATS comes in. So I kind of wear two hats. One is my day job at CMU as chemistry professor. The other is running the startup that I founded with a collaborator in the machine learning department at CMU. We are broadly interested in the question of, since most chemical products ranging from shampoo to concrete are mixtures, we're broadly interested in developing machine learning models that will help people sort of design these, in terms of, sort of the general question of, I've got this set of ingredients and I want this set of properties. How do I mix and match these? And so there are in some very high level ways that making shampoos is actually relatively similar to making concrete. And so we started with building a model for compressive strength. And so one thing that the software does that we've built is it starts to represent these formulations as graphs. And so in a graph, the nodes, the circles are objects, and then the edges or the lines are relationships between objects. And so what this graph is doing is, so these are the literal ingredients that you would use you could add in order to make a CC1L type cement. And then all it's really illustrating is I've got a lot of ingredients and every one of them is probably interacting with each other. It does allow for you to ask certain questions. So for example, if you wanted to ask, what is the relationship between the superplasticizer and the clay, for example, you might be really interested in the structure of that edge and the factors that control it. But what the graph lets us do is it lets us start to come up with representations and focus in on specific aspects of these complex formulations. We can flip that to a roles graph where essentially roles winds up being the more generic label in terms of a pozzolan could be lots of different things, and you might actually have multiple pozzolans blended into one sample, but they're all playing the role of pozzolan, and the role of pozzolan is different from the role of clinker, for example, or the role of calcium carbonate. And so what we've seen, and again, one thing the software does is there's just a button, you press it, in the background a bunch of machine learning models get generated and the most accurate one gets displayed. But what we're seeing here is these are, again, the parity plots. And again, what it looks like is that the model has actually really started to learn based on the data that Daniel's collected. It's really started to learn sort of what are the factors that really govern the mortar strength of these CC1L type, based on CC1L cements. You can do things like look at the features that govern this, and this is where we start to, so it's not surprising that the most important feature is time. So in case, you heard it here first, it turns out cement gets stronger as it ages, and so machine learning was able to prove that definitively here. There are a lot of other factors that enter into this, and then there's some that, so obviously like the model right now for strength really believes that the amount of magnesium oxide present in these samples, which is small, really matters. And so there are going to be some things that there's something hiding behind that. There's a variable hiding behind that we're starting to tease out. But right now we've got a way of representing this in terms of a combination of different variables such that if you knew some of these different features, you could be able to make very broad predictions about strength. And then looking at mortar flow actually has a much more complex graph. A lot of things enter into determining how that looks. And so if we switch to the roles graph, it winds up being simpler. The water to binder winds up isn't connected to the graph just because we held it constant throughout all the different experiments, and so it just shows up there. But we have no way of learning what the relationship with these other features is. And similarly, the model is doing a pretty good job of learning some of the basic trends that govern mortar flow. We see a good connection between the two parts of model development, training, and testing, suggesting that we are learning some of these more reliably. Here, the most important feature is just the dose of the superplasticizer. So we haven't even delved into the chemistry of it, but certainly the model has figured out that the amount of superplasticizer is important. It's interesting, though, that it really is focused in on the variables associated with the clay. So both the size distribution of the clay, so what we're reporting is D10 in microns, but then also the amount of metakaolin is showing up as highly important in terms of determining the mortar flow. And then finally, this is just some technical details. What it's kind of pointing to, though, is when we look across multiple models, training is the part where the algorithm knows the samples that it's looking at, and then all it's trying to do is make the best fitting model possible. In validation, you withhold unseen samples, and then you ask it, you basically test it, how good are you at predicting something you haven't seen before? And there's a real variance and generally kind of oftentimes a drop-off in performance. And so what that suggests is that the model is still kind of what we call overfitting. It's kind of latched on to certain characteristics that are very specific for the samples that it's looking at. It's one indication that we haven't quite finished the job with feature selection, and we probably need more samples, which are coming from Daniel and others. But anyway, I just want to, in conclusion, we do think that machine learning is turning into a helpful tool in terms of, there was a very interesting AI session earlier that Bolshin's in the back, who was chairing that. Hope there will be a second session this afternoon. But we do think that machine learning can help with some of these problems. I think the challenge is the complexity that some of the solutions to the problems winds up introducing. And so we're looking at, we are trying to take baby steps as far as employing data science in starting to model and understand how these systems work. I really would like to thank Cajun and her team at Iowa State for leading this giant effort. And then Kim and Maria also for their help with our particular part of the project, and I'd be happy to answer any questions.